Good morning. My name is Peiris. I will be going over about the investigation of robotic arm tracking of infant reaching actions. To start, in this research, the main objectives are investigating whether the robotic arms can follow the infant trajectories, and if they can follow the trajectories at the same rate, and determine how smooth these trajectories can be, and establish an effect of the configuration space, which is the robotic space where the robotic arm can move, and velocity constraints of the robotic arm. And after this, the goal of this is to track infant reaching trajectories in real time using a softwareable robotic device, and ensure the robot can capture the temporal component of infant reaching and use that ability to close a real-time control loop to offer assistive feedback. And then to begin, for background, this is mainly used in human-robot interaction, which is a communication between the human and the robot. Currently, it's established in social and physical settings to assist the human and in rehabilitation. And humanoids are robots that are similar looking to humans. And as you probably know, there are 2 robotic arms for each. And these robotic arms are used in the settings of reaching, grasping objects, handshaking, passing objects, kitchen work, or sport activities using adult data. And so my methods are to track data from the infants, transform the starting point of these trajectories, calculate the inverse kinematics to get the joint angles so I can move the arm towards the points taken from the trajectories, and then publish these joint angles to the robot and take that position from the robot and then plot it to see and compare the performance of these reaches. And my data set includes 18 videos and 18 infant subjects with 16 neurotypical subjects and 2 neurodivergent subjects. I'm using only 60 reaching actions, but currently we have about 437 reaching actions. The main reason I'm only using 60 is because in order to use the data, it has to be calibrated into centimeters. And since I'm using videos, we only get 2D data, so it has to be, when calibrated, both the arm and the calibration object has to be on the same frame as the reaching action. And then I'm only taking reaching actions where the infant is performing the reach on a side view or in the same frame, not like this. So it has to be, the reach has to perform like this in the video. And these infants range from 5 to 12 months. And as you can see in the plot here, this is the distribution of the reaches with the total number of frames and the number of reaching actions. And then here, these images are taken from Kinematics, a manual annotation software. So to perform tracking, in the first image, onset is the very first frame where the infant moves the hand towards the object, and the offset is the very first frame where the infants touch the object. And you track from the onset to offset using Kinematics. And this is one from during the reach. And if you can see, the yellow line shows the trajectory. And in calibration, so this tracking is, the tracking data is taken from given pixels and we need it to be centimeters. So we calibrate the data using the inference cornea or an object that is on the same frame as the trajectory. And after that, the 60 regions are, you can see here, the original data looks like this. It is a range, the x-axis range for 70 centimeters and the z-axis range for about 60 centimeters. But when we use this data, because it has a lot of negative numbers, the robot tend to collide with the arm collide with the robot base. Because of that, we transfer all the data to one point, which is 0, 0, 0. And then through trial and error, we figure out that the best starting position for the robot is x to be 0, y to be 15 centimeters, and z to be 20 centimeters. And after that, we calculate the inverse kinematics. So this is an image of the one of the robots I'm using. I'm using ReactX 150 and ReactX 200. The difference between the two robots is both are exactly the same, just this link and this link that shows 150 is 200 in ReactX 200. And to move the arm to each point, we calculate theta 1, theta 2, and theta 3 here, because the our end effector is at joint 4. So I will be moving joint 4 to according to the region trajectories. And here, this is input to the red, it shows the input to the robot, which is taken from the trajectories. And blue shows the output from the robot, which is subscribed from the robot. So we know where the end effector is. And so these are the plots plotted like this. And then the bottom two rows is the Bland-Almond plot. And in X, it shows the mean, and Y, it shows the standard deviation. And so this dotted line, it shows a 95% limit of agreement around the mean. And then if you can see here A, C, and D, you can see there's a higher correlation on the points. But that does not mean it's always good, because if you see in A and B, when closer to the end, the trajectory doesn't end well. So because of this, we use mean squared error plots. And this is for ReactX 150, and this is for the ReactX 200. As you can see, there are differences between the two plots because of the difference in the length of the robot. And this, so I took these plots in 4 different rates of the robot. So the yellow shows the original rate where the data has been collected, and the red, orange, and the gray one are lower rates than the original. So the top 2 plots show the plots for ReactX 150. The main reason there are 2 big spikes here is because in 2 of the reaching actions, it goes out of bounds, and the robot, the arm goes to 0 and it doesn't move during those 2 reaches. And here you can see, here the arm goes out of bounds, so it goes to 0. That's why there are 2 spikes here, because the z goes to 0. But in ReactX 200, it performs all the trajectories. But the main reason the yellow is fluctuating is because the larger the arm is, there's more torque. So it's hard to move compared to the arm that is shorter. And these are some rates. So 30.5 is the original rate, and 10 is a lower one. So original rate, it skips some of the points, and in 10, it doesn't. And to conclude, the infants, we can hold the arm instead of going to 0 in the same position till it enters a reachable workspace, or predict the arm's movement for the missing data. And one is to find the rate that minimize the errors of missing data, but not too slower. And for future, we plan to use this in simulation for the physical robot and cooperate with the software robot. I would like to thank my PIs, Dr. Elena Cocconi and Dr. Constantinos Carides, for guiding me, and the PhD student Ipsita Sahin for helping me throughout the project, and the PRT and ARCS lab. Thank you. Do you have any questions?
Thank you. That was great. And you can go ahead and stop recording.